Welcome to another AI pattern recognition deep dive.
If you have interacted with technology, well, at any meaningful level in the last decade, which, let's be honest, means if you're listening right now, you've left behind this huge digital footprint. Today, we're really digging into the invisible architecture, the system that takes that footprint, your clicks, your actions, your purchases, and transforms it. Transforms it into this profound mathematical prediction of who you are.
Yeah, and not just who you are now, but what you desire, what patterns really define your behavior.
Exactly.
And that transformation, that's really the core of what our source material is exploring today. The explosive power of modern AI, it touches absolutely every part of human life now, right? Family, finance, everything.
Everything.
And it all stems from this one ability: recognizing, classifying, and crucially predicting complex patterns. And these patterns are hidden in these massive, really diverse data sets.
And the mechanism itself is key here, isn't it? How it turns our raw behavior, this sort of digital residue.
That's the critical insight, yes. AI fundamentally takes that raw behavior and translates it into numbers, into numerical representations. And those numbers are then used to estimate some really deep psychological characteristics.
Like what kind of characteristics?
Well, things like intelligence or predicting mental health status, even mapping out core personality traits. It's quite profound.
Okay, so our mission today, it feels like it's got three main parts, and it definitely needs some close scrutiny. First, we need to unpack the architecture itself.
Right.
The engine room, how this thing actually works.
Right, the foundations.
Second, we need to look at how it's being used now, how it's shaping, sometimes disrupting our social lives, our work lives.
The immediate impact, yeah.
And finally, and this feels really vital, we have to analyze the ethics, the governance structures that we need to make sure this is deployed in a trustworthy way. We need to understand the limits, of algorithmic accountability.
Absolutely. Because the whole landscape has shifted. The sources are clear on this. AI isn't just some niche tech tool anymore. It's not operating off in a corner.
No.
It's become a fundamental operational structure of modern society. And if these pattern recognition systems are deciding things like who gets credit or access to education or even influencing our social connections,
then we absolutely have to understand the mechanics inside that engine room, the things dictating those outcomes. Okay, let's start right at the beginning. The fuel for this engine. For any pattern recognition to work well, you need data. Lots of it.
high volume data, yeah. But just as importantly, it needs to be diverse data.
Diverse in what way?
Well, it's not just about reading, say, one type of financial ledger. It's about collecting data in lots of different formats, often simultaneously, and then being able to kind of stitch them together seamlessly.
And it's that holistic view, that combination, that lets the real patterns emerge.
Precisely. That's where the power comes from. Our sources point to four main types or modalities of data that these AI systems have to manage and synthesize. First up is text and natural language.
Okay, so emails, social media, transcripts.
Exactly. The whole vast corpus of human communication that's been digitized. Think emails, posts, customer service chats, massive document libraries. It's huge.
And there are patterns here. It's not just what you're saying, but how you say it, right?
Absolutely. The AI is looking at linguistic patterns. It can classify documents, sure, but it can also determine sentiment. Is this customer review positive or negative? It can even do quite detailed fraud detection based purely on linguistic cues.
Like how? What kind of cues?
Subtle shifts in vocabulary, maybe changes in formality that are unusual for that person, or even just unusually rapid communication patterns compared to their baseline. The language itself contains signals.
Interesting. Okay. What's the second modality?
Second, and this one is really vital for prediction, is time series data.
So things that happen in sequence over time.
Exactly. Time-stamped information, click streams on a website, outputs from sensors, system logs, your financial transaction history, anything where the order matters.
And why is that so crucial for forecasting?
Because the data points are strictly chronological, the AI can model those temporal relationships. It can learn patterns over time. So you use this to analyze, say, someone's purchasing behavior over weeks or months to predict their risk of churning, leaving the service.
So it's not just what they bought.
No, it's when they stopped buying, or maybe when their interaction frequency suddenly dropped below their normal level. The pattern is that sequential consistency, and it's the disruption of that sequence that becomes the important signal.
Okay. Makes sense. Third type.
Third, we have video streams. This brings together visual information with that time sequencing element.
Right, like security cameras.
That's a major application, yeah. Real-time behavioral analysis. Think about monitoring retail stores or warehouses using those feeds. The AI learns the pattern of normal movement, normal interaction.
And then flags anything unusual.
Exactly. When a deviation occurs, someone moving maybe unusually fast, or entering an area they shouldn't, or maybe exhibiting behaviors that historically correlate with theft, it flags that anomaly instantly. It's detecting a break in the established visual pattern of normalcy.
Okay, and the last one, the bedrock.
And finally, yes, the structural bedrock, structured tabular data.
Your classic spreadsheets and databases.
Pretty much. The traditional records, data organized into those neat, consistent rows and columns. Your grades in school, survey results, the entries in a CRM system, bank account ledgers.
It sounds less dynamic than the others.
It can seem that way, but the structured data often provides the crucial context. It's often the ground truth against which the patterns found in the other messier data types are validated.
So the big architectural takeaway here isn't about any single data type, is it?
Not at all. The real power is in the combination. An effective system, let's say one identifying risk in a global supply chain, isn't just looking at one spreadsheet.
Right.
It's probably combining structured logs of inventory levels with time series data on shipping delays pulled from GPS and unstructured text analysis from news feeds about port closures or supplier announcements.
You need all of it.
You need all of it. The deep, meaningful patterns that drive modern AI, they just don't emerge if the data stays stuck in isolated silos. You have to bring it together.
Okay, so we've gathered this enormous, messy, multimodal data set. What's next? The system needs to make sense of it, impose some structure. You mentioned feature extraction.
Yes, feature extraction. This is the absolutely critical next step.
Why is it so crucial? What's it actually doing?
Well, think about that raw data. It's overwhelming. It's full of noise, irrelevant details, stuff that doesn't actually help predict anything. Feature extraction is the process where the architecture intelligently reduces that complexity. By isolating the characteristics, the features that actually carry meaningful predictive information for the specific task at hand, it's about separating the signal from the noise.
Can you give an example?
Sure. If you're trying to classify an image, the features the AI extracts might start with raw pixel values, then move to recognizing simple edges, then combinations of edges forming shapes, and then maybe specific objects. Each layer extracts a more abstract, more meaningful feature.
Okay. And you mentioned this is a key point for governance. This data pre-processing, specifically feature engineering, that's where the human element is really strong.
Absolutely. Our source material is very explicit about this. Feature engineering is a primary point where governance needs to focus. This is where human analysts decide which attributes, which characteristics from the raw data to actually feed into the model.
And that decision can introduce bias.
Hugely. If the analysts, even if they don't mean to, select features that happen to be proxies for protected characteristics, like, say, using someone's zip code or neighborhood name.
Which often correlates strongly with socioeconomic status or race.
Exactly. If you use that as a feature, then bias gets baked into the system's design before the AI model even starts learning. The pattern the AI subsequently learns will inherently reflect that historical correlation, that proxy bias.
Wow. So it's not just a technical step, it's a fundamental structural decision with major ethical implications.
It really is. What you choose to measure, what you choose to ignore, defines the entire ethical trajectory of the model that follows.
Okay, that's a crucial point. Let's move on to the processing units themselves. How does the AI actually use these features to find the patterns? We need to get a handle on the core neural architectures.
Right. We can start with a foundational one, the multi-layer perceptron, or MLP.
Yeah.
You can think of an MLP as basically a series of connected processing layers. The features you extracted, they go into the input layer, then they travel through one or more hidden layers, and finally, they reach the output layer, which gives you the classification or the prediction.
So it's like a step-by-step decision process.
Yeah. In essence, yes. It's a baseline deep learning architecture. Each layer learns to recognize successively more abstract patterns based on the outputs of the layer before it. It's building up complexity step by step.
And the basic unit doing the work in those layers is the neuron. How do these individual units operate? Is it like a brain neuron?
Well, the analogy is helpful, but it's simplified. The mechanism of an artificial neuron is actually quite elegant. The key part is the activation function. It determines the neuron's output signal. A good analogy our sources use is that it acts like a light switch with a dimmer control.
Okay, a dimmer switch. How so?
The incoming signal, based on the weighted inputs from the previous layer, has to be strong enough to even flip the switch on. That's the activation threshold. But then the dimmer control adjusts the strength of the output signal that gets passed on.
So it's not just on or off.
No,
Yeah.
this dimmer allows the network to learn which inputs are really important for the current pattern and which are less so. It learns to emphasize certain features and diminish others.
So going back to the shopping example,
Mm.
maybe high spending on, say, specific niche hobbies would activate a neuron really brightly,
Right.
while something common like occasional grocery spending might just be dimmed way down because it's not very predictive of a unique pattern.
Exactly right. That selective focusing, that dimming and brightening is crucial. It lets the network filter out the noise automatically while combining and synthesizing the complex relationships hidden in that incoming data. And then the next hidden layer takes the output of all those dimmed lights from the previous layer and uses that as its input to find even more abstract patterns.
Okay, so you're building up from simple correlations to these really deep behavioral insights layer by layer.
That's the core idea of deep learning, yes.
That MLP architecture sets the stage. But the real, paradigm shift in pattern recognition lately, the thing powering models like GPT, Claude, Llama, that's the transformer architecture, right?
Yeah.
What was the big leap forward there?
Oh, the transformer was and is a massive deal. It fundamentally changed how AI understands sequence and context. Its real strength is recognizing patterns in sequential data text is the obvious one, but also code, speech, even sequences in video by learning the context of every element in relation to every other element in the sequence.
Even ones that are far apart. That was the problem with older models, wasn't it? Forgetting the beginning of a long sentence.
Exactly. Older recurrent models struggled with those long-range dependencies. The big innovation in the transformer was replacing those recurrent units with something called the self-attention mechanism.
Self-attention.
Yes, and crucially, this mechanism allows the model to process all parts of the input sequence in parallel at the same time, rather than step by step. This made training much, much faster and allowed for the creation of these enormous models with billions of parameters.
Okay, so the challenge is context. In a sentence, the meaning of a word early on might depend heavily on a word much later. How does self-attention model that connection?
This is where the genius lies. And it's based on what's called the Query Key Value QKV model. It sounds technical, but the concept is quite intuitive.
Let's break it down.
Okay, so first, every piece of the input, like a word or maybe part of a word called a token, gets converted into a numerical vector, an embedding. This vector captures its meaning, its semantic essence.
Right.
Then, for the attention calculation, the model derives 3 new vectors from that original embedding for each token. These are the query, key, and value vectors.
Okay, query key value. What does each one do?
Think of it like this. The query vector, Q, represents what this token is looking for. It's asking the question, which other tokens in this entire sequence are relevant to understanding my meaning right now?
Okay, it's seeking information.
Exactly. Then the key vector, K, represents what information this token offers. It's like saying, here's the kind of relevant information I contain if any other tokens are looking for it.
So Q is asking, K is advertising what it knows.
A good way to put it. And the interaction between them determines relevance. The core function is the alignment, mathematically, between a token's query Q and another token's key K.
And if they align well.
If a query finds a key it matches well with, it generates a high attention weight between those two tokens. This weight essentially says, these two tokens are highly relevant to each other. Pay attention to their connection.
Even if they're far apart in the original sequence.
Especially if they're far apart. That's the power. It allows the system to directly link data elements regardless of their position, and the value vector, V. That contains the actual substance, the semantic content of the token that gets passed along, weighted by that attention score.
So that attention weight acts like a spotlight, highlighting the important connections across the whole sequence.
Precisely. And you can see how critical this capability is for modeling complex human patterns. Think about tracking someone's shifting political views expressed on social media over 5 years. The transformer can learn the contextual links between a statement made years ago and, say, their purchasing patterns today. It doesn't just see a linear sequence. It sees this intricate web of interdependencies that reflects long-term, complex human traits and histories.
Okay, so when you get that level of sophisticated pattern recognition, linking data points across years, building these complex webs, you inevitably end up with models that have You said billions of parameters.
Easily, yes, the scale is immense.
And that leads directly to this huge governance challenge,
Yeah.
the black box problem. We build this incredibly powerful thing, but we can't actually look inside and see why it made a specific decision.
That opacity, that lack of transparency, is a fundamental barrier to deploying these systems responsibly, especially as we discuss when the AI is classifying really sensitive traits, things like deriving psychological profiles from your financial data or your online activity.
Right. If a model denies you a loan or flags you for some kind of risk based on a pattern it recognized, accountability demands we know how it reached that conclusion.
It absolutely does. And this necessity is what mandates the structural integration of explainable AI, or XAI.
XAI. So this is the framework we need for humans to actually validate what the AI is doing.
Exactly. It's about providing tools and methods so that domain experts, whether that's lawyers, psychologists checking if a profile makes sense, or managers understanding a workplace recommendation, can audit and verify the patterns the AI claims to have found. It brings human judgment back into the loop.
How does XAI work? Are there different levels of explanation?
Yes, it generally operates at two key levels, and this duality actually creates a bit of a governance tension, but both are needed. The first level is global rule extraction.
Global, meaning for the whole model.
Yes. This aims to explain the model's overall logic. What are the general patterns the model found most predictive across the entire dataset for a particular outcome? It gives you a high-level view of the model's thinking.
Can we make that more concrete? What would a global rule look like?
Sure. Let's say an AI is predicting creditworthiness. A globally extracted rule might reveal that the model heavily weights a set of features related to, say, high frequency of taking out small short-term loans.
Okay.
The extracted rule might look something like, if microloan frequency per year is greater than X, then classify as high default risk. This kind of global rule allows policy experts, economists, regulators to check if the model's general logic aligns with established economic principles or fairness guidelines.
And if the rule seems weird or discriminatory?
Then they know the model needs investigation or retraining. It's a sanity check on the overall strategy.
Okay, that's vital for policy and strategy. But you mentioned attention. What about the individual person affected by the decision?
Right. That's where the second level comes in, and it's arguably even more critical for fairness and individual rights, local explanations. These are specific to one particular instance, one individual prediction.
So why did I get this specific outcome?
Exactly. Local explanations are non-negotiable for genuine accountability. They need to show precisely why an individual received a specific classification, denied the loan, flagged as high risk based on their unique combination of data inputs, their specific spending, their specific online behavior.
And how do you generate that kind of specific explanation?
There are various techniques, but one that the source material really emphasizes as ethically vital is the counterfactual explanation.
Counterfactual. Like what if? It sounds like this gives the person some agency back.
It absolutely does. That's the point. A counterfactual explanation identifies the minimal changes that would need to be made to that individual's input data. Maybe their spending history, their interaction frequency, their answers on an application to achieve a different, usually more favorable outcome.
So it's actionable.
Yes. You can't just tell a student, our AI predicts you're likely to drop out. That's not helpful. A counterfactual explanation would say something like, if you had increased your time logged into the learning platform by 15% and submitted all assignments on time last semester, your predicted attrition risk score would have shifted from high to moderate.
Wow. Okay. So if the AI is built to recognize and predict my patterns, the counterfactual explanation literally gives me the instructions on how to change that pattern to get a different result.
Precisely. It empowers the individual to understand and potentially challenge the algorithmic judgment.
So the structural tension is clear. You need the global explanations to validate the overall policy and ensure the model isn't fundamentally flawed, but you absolutely need the curriculum, local, especially counterfactual explanations, to ensure individual fairness, provide recourse, and operationalize basic human rights in an automated system.
And effective ethical governance means constantly managing that tension, demanding both levels of explanation.
Okay. Understanding the architecture, the engine room, and the need for explainability takes us squarely into the applications. Where are these pattern recognition systems actually being used, and how are they changing things? Let's start really close to home. Interpersonal dynamics relationships. family, friends.
Yeah, this is where the implications get very personal very quickly. The ability of AI to take that messy digital footprint and translate it into surprisingly accurate estimates of deep psychological traits is, well, it's transformative and often completely invisible to the person being analyzed.
You mentioned a case study.
Yes, the sources highlight one where researchers successfully used only financial transaction data, what people bought, where they spent money, the frequency to train an AI, and that AI learned to identify spending patterns that correlated strongly with established psychological models, specifically the Big Five personality traits.
Wait, just from credit card bills. It could map personality.
That's what they found. The AI recognized patterns in consumption. Maybe high spending on travel and social events correlated strongly with high extroversion scores. Perhaps meticulous budget tracking and high savings rates correlated with high conscientiousness.
That is kind of astonishing. Your spending habits become this passive personality test you didn't know you were taking.
Exactly. And think about the implications. Targeted marketing is the obvious one, but it goes deeper. Targeted influence, political messaging tailored to your personality profile derived from how you shop.
And it's not just profiling us, it's changing how we interact, right? These incredibly articulate chatbots and virtual assistants.
Definitely. We're seeing the rapid rise of what sociologists call parasocial relationships. These are one-way emotional connections people form with media figures or now with AI. You feel a connection, but it's not reciprocated.
And there's a boundarylessness.
Yeah, people tend to interact with these advanced chatbots with fewer social boundaries than they would with humans. Because the AI can mimic empathy and relational patterns so well, users often extend trust and vulnerability quite quickly. This whole effect gets amplified by our natural tendency towards anthropomorphism.
Attributing human traits to the AI.
Right. We start treating it like a person, which makes us more likely to accept its suggestions, follow its advice, integrate it into our social routines.
What's the bigger societal consequence of that shift if we rely more on AI for connection?
Well, it subtly starts to shift our core social norms. Think about traditional human relationships. They rely on reciprocity, on mutual understanding, politeness that's expected back. When an AI perfectly mimics the behavior of a good relationship partner, listening, remembering details, offering support, but offers no genuine emotional reciprocity, it can actually change users' expectations for human interaction. Some research suggests over-reliance could potentially lead to a gradual erosion of collective empathy or social cognition skills, because the baseline for good enough interaction gets subtly lowered to something automated and non-reciprocal.
That's a sobering thought. Okay, zooming out a bit to the macro-level social impact. Algorithmic polarization. The source material seems pretty clear that social media algorithms aren't just reflecting polarization, they're driving it.
They are positioned as active agents in this process, yes. The pattern recognition models inside platforms like Facebook, TikTok, YouTube, they are fundamentally optimized for one thing: engagement.
Keeping you on the platform longer.
Keeping you clicking, reacting, sharing. And the most effective way they found to do that is to analyze your past consumption patterns, what you watch, what you like, what you comment on, and then curate your feed to give you more of the same, even more intense versions of the same.
So it finds the pattern of your existing beliefs or interests.
Exactly. It recognizes the specific ideological or emotional patterns you respond to, and then it feeds that pattern back to you, often amplifying it.
So the fact that you end up seeing fewer and fewer opposing viewpoints, that's not an accident. It's baked into the optimization.
It's a direct consequence of the pattern matching feedback loop. By constantly reinforcing your existing biases and actively algorithmically restricting your exposure to differing views because they don't match your engagement pattern, the AI becomes an active facilitator of polarization.
It's creating these echo chambers or filter bubbles.
Worse, the sources describe them as isolated ideological ghettos, where the recognized pattern of your belief system is just constantly confirmed, often radicalized by this automated curation engine. It makes finding common ground much harder.
Okay, let's shift the lens now to the workplace. Organizational dynamics, coworkers and management. How is AI pattern recognition changing how businesses operate and how people work together?
One of the more, perhaps, insidious risks that the sources identify here is the potential erosion of social capital.
Social capital, meaning the trust in networks between people.
Precisely. We know that high-performing teams aren't just about individual skills, they're differentiated by the strength of their informal networks.
Right.
That peer trust, the easy knowledge sharing, their reciprocal support, I help you, you help me.
Right.
When employees start to rely heavily on AI systems for quick answers, for drafting emails, maybe even for venting frustration or seeking advice, they start bypassing those crucial human peer networks.
The AI becomes the go-to instead of your colleague next door.
Exactly. If the AI becomes the most efficient or even the most supportive coworker, that algorithmic dependency can start to fundamentally alter human trust and collaboration patterns within the organization. The structural patterns of those vital informal networks, which are key for innovation, problem solving, and resilience, can begin to weaken, to atrophy.
The knowledge might still get transferred, but the social glue dissolves.
That's a good way to put it. The social capital itself is compromised.
And meanwhile, management is using AI to actually map these networks, right? Automated influence mapping.
Yes. Traditionally, mapping workplace networks, figuring out who really influences decisions, who are the key connectors, involve things like organizational network analysis, O&A. But that was often slow, expensive, relied on surveys.
Now AI does it automatically.
Instantly and continuously. By analyzing digital communication, flows, the patterns, and who emails whom, how often, who's included on calendar invites, usage patterns and collaboration tools like Slack or Teams, even who collaborates on shared documents, the AI can map the real network.
Not just the org chart.
Not just the org chart. It sees who talks to whom, who relies on whom for information, who might be a bottleneck in communication flow, who the real informal influencers are. This allows management to understand productivity and influence patterns in a way they never could before, potentially shifting power dynamics away from formal titles towards observed digital interaction patterns.
Hey, let's move into education and pedagogy. This seems like a field ripe for pattern recognition, especially for tailoring learning.
Absolutely. This is where we see some incredibly sophisticated applications, particularly in adaptive learning systems. The entire structure of these platforms is often designed to personalize the learning journey by continuously modeling and assessing a student's dynamic skill level in real time.
How does it model something as fluid as learning?
A foundational architectural framework used here is Bayesian knowledge tracing, or BKT.
BKT. Sounds complex. Can you break down how it works conceptually?
Sure. BKT is essentially a probabilistic model. Its core job isn't to give a student a fixed grade, but to estimate the probability that the learner has mastered a specific skill or concept. Let's call it PL, the probability of learnedness.
Okay, a probability, not a fixed state.
Right. And it's constantly updating this probability for every skill being tracked. Every single interaction the student has with the learning material, every question they answer correctly, every mistake they make, even how long they take to answer, provides evidence to update that PL score. It's a continuously evolving, fluid assessment.
So it's recognizing the pattern of their learning process, the trajectory, not just the final answer on a test.
Exactly. It's tracking that dynamic state of mastery. And this real-time tracking is what dictates the next step in their learning path. If the probability of mastery for a concept is high, the system might accelerate, introduce a harder topic. If PL drops, it might loop back, offer reinforcement, maybe a different type of explanation.
It's adapting the pace, sequence, difficulty based on that recognized pattern of understanding.
Precisely. It's a structure built around dynamic state recognition, assessing a constantly changing state rather than assigning someone to a fixed category.
And the sources mentioned this structure is highly transferable.
Immensely so. The core mechanism probabilistically tracking an evolving state, whether it's competence improving or something deteriorating, is valuable in many domains beyond education.
Like what?
Well, the same fundamental architecture can be applied to assess military troop readiness based on training data, or monitor employee fatigue or burnout risk based on communication or activity patterns, or track a patient's health status in real time in a hospital based on sensor data. In all these cases, the AI learns a normal pattern and then continuously updates the probability of being in a particular state, ready, fatigued, healthy, deteriorating, based on incoming time-sensitive data.
Beyond tracking mastery, AI in education also uses predictive analytics to flag potential problems, right?
Yes, this is a huge area. By analyzing detailed engagement patterns, not just grades, but things like how long students spend wrestling with specific types of problems, how often they log in, the kind of errors they make, are they careless mistakes or fundamental misunderstandings, AI models can predict future performance outcomes.
And crucially, predict who might be at risk of dropping out.
Exactly. Attrition risk is a major focus. The goal is to identify students who are starting to show patterns associated with disengagement or failure early enough for teachers or advisors to intervene. A targeted human conversation triggered by the AI's pattern recognition can make a huge difference.
But this predictive power, especially in education, brings up a really serious ethical concern you flagged: algorithmic determinism.
This is a profound worry, yes. If these adaptive learning systems rely too rigidly on a student's past performance patterns to predict their future potential.
They risk pigeonholing them.
Precisely. If the pattern the AI recognizes suggests a student has hit a ceiling in, say, math, the system might automatically steer them away from more challenging math-related subjects or careers. It might inadvertently deny them exposure to areas where they could have potentially excelled later, maybe after a different kind of breakthrough or teaching approach. The system predicts, based on the past, potentially limiting the future.
So the governance challenge here is to build systems that allow for surprises, for growth that breaks the past pattern.
Exactly. Educational AI governance has to actively build in mechanisms that account for human potential, for unexpected leaps, for late bloomers. It needs to resist locking a learner into a trajectory based solely on the predictive patterns extrapolated from their past struggles. It needs to allow for positive deviation.
Okay, turning now to strategic security and governance. Obviously, in military contexts, pattern recognition is huge for analyzing intelligence data, quickly geospatial signals, imagery.
Yes, speed and scale are critical there. But a foundational structure used across many security and industrial applications is anomaly detection. A really powerful common example is in predictive maintenance.
For machines, like jet engines.
Jet engines, power grids, critical IT infrastructure, complex manufacturing equipment. The architectural approach is usually quite strict, involving 3 steps. First, baseline training. You rigorously train the AI models only on data collected when the system is operating normally, when it's known to be healthy. This teaches the AI the precise pattern of normal.
So it learns what good looks like in minute detail.
Exactly. That pattern of normalcy is the absolute key. Second, you deploy specialized models, often things like autoencoders or isolation forests, whose specific job is to spot significant deviations from that learned baseline pattern.
Okay.
Third, real-time monitoring. As new sensor data comes in, vibration, temperature, network traffic, whatever it is, the model compares it against the learned pattern of normal. If a data point or a sequence falls significantly outside the acceptable parameters of that pattern,
It flags it as an anomaly.
instantly, alerting human operators to a potential problem, maybe an imminent equipment failure, long before it becomes catastrophic.
Now, here's a really critical point you raised, the dual-use implication. This same architecture, learning normal, detecting abnormal, it can be applied to people.
And this is where it gets very sensitive, and the sources urge extreme caution. The mechanism is identical. Step 1, learn a baseline pattern of normal human operational behavior in a specific context, e.g. workplace activity. Step 2, deploy models to detect significant deviations from that personal or group baseline.
What kind of deviations?
It could be anything the system is trained to monitor. Abrupt changes in someone's communication frequency or timing, unusual patterns of accessing files or buildings, significant shifts in financial transaction patterns compared to their history, changes in tone or sentiment in written communications.
And this could be used to detect things like insider threats, burnout.
Those are exactly the kinds of applications discussed, detecting anomalies in human behavior that might correlate with insider risk, critical levels of burnout or fatigue that could compromise safety, or even potentially health issues. The capability is there.
Which means the need for rigorous guidelines, oversight, and ethical review for any such system is astronomical.
Absolutely paramount, because the pattern being tracked is intensely personal, and the potential for misuse or misinterpretation is enormous.
We're also seeing governments use these kinds of pattern recognition capabilities, right? You mentioned the German OLGA bot for legal expediting.
Yes, using AI to automatically categorize legal cases or documents to help manage huge backlogs more efficiently. It recognizes patterns in case descriptions or legal arguments to sort them.
But this efficiency gain comes with that huge warning about bias acceleration.
This is a critical danger highlighted in the sources. If the historical data used to train these categorization models, like past legal case files, contains systemic historical biases.
For example, if certain demographic groups were disproportionately arrested or given harsher sentences in the past, due to biased policing or judicial practices.
Exactly. If that bias exists in the training data, the AI will learn that pattern as if it's a legitimate correlation. It will learn, essentially, people from group X are higher risk. And then it will apply that learned pattern with ruthless, automated efficiency across all new cases it sees.
So the algorithm doesn't just replicate the past bias, it amplifies it and makes it systematic.
It accelerates the propagation of that historical inequity. What might have been inconsistent human bias becomes codified, scaled up, and applied instantly by the algorithm. The efficiency gain directly translates into faster, wider application of the underlying historical injustice.
Okay, the influence of these pattern recognition models clearly extends beyond individuals and organizations into these huge, complex, almost chaotic macro-societal systems. Let's start with the macroeconomic impact. Neural networks are being used in finance for what exactly?
Well, they're identifying subtle, nonlinear patterns that older statistical models like linear regression just couldn't see. This allows for potentially more accurate predictions of stock market fluctuations, much more sophisticated detection of complex, networked financial fraud, and more nuanced appraisal of insurance risks. They find correlations hidden deep in the data.
But there's a unique governance challenge here, isn't there? Something about the system influencing itself.
Yes, the self-fulfilling prophecy of trading. This is a fascinating and slightly terrifying feedback loop. It happens when a large number of institutional investors all start using sophisticated AI models trained to recognize similar subtle patterns that supposedly predict an impending market shift, say, a particular configuration of indicators suggesting selling pressure is building.
Okay, so multiple AIs spot the same sell signal pattern.
Right. And because these are often automated trading systems, they act on that recognized pattern almost instantly and collectively. They're coordinated selling action triggered by recognizing the pattern.
Can actually cause the market drop they were predicting.
Precisely. The very act of recognizing the pattern and acting on it, when done at scale by enough powerful players, creates the market reality it foresaw. The prediction becomes self-fulfilling.
So the AI isn't just reacting to the market, it's driving it in potentially unstable ways.
It introduces a new kind of systemic financial risk. Market volatility isn't just about economic fundamentals or news events anymore. It's also driven by the emergent collective behavior of these automated pattern-seeking algorithms interacting with each other. This necessitates really stringent governance, things like market circuit breakers or rules demanding transparency around the use of certain high-frequency trading algorithms.
Okay, turning to the political threat landscape, we talked about AI driving polarization on social media.
Yeah.
But it's also being used to analyze political discourse itself.
Yes, beyond just basic sentiment analysis, AI is enabling much more detailed discourse analysis. This involves analyzing massive amounts of political speech, social media conversations, news articles, etc., to model and track patterns of discourse homogeneity.
Homogeneity, like how similar people talk within a group.
Exactly. The AI can identify how similar the vocabulary, the emotional tone, the core arguments, the recurring themes are within one ideological subgroup compared to another. It gives you a quantifiable measure of how fragmented the political conversation is, how rigid the boundaries are between different groups based on their distinct linguistic patterns.
And then there's the more direct threat, leveraging that transformer architecture we discussed, contextual disinformation.
This is where it gets truly insidious. The very strength of the transformer, its ability to understand deep context and nuance, can be weaponized. An adversary can use AI to recognize the precise cognitive and emotional patterns of a specific target group or echo chamber.
What patterns?
The language they use and trust, the news sources they believe, the emotional triggers they respond to, their inherent biases, the narratives that resonate with them. The AI learns the pattern of their worldview.
And then crafts messages specifically for them.
And then generates hyper-contextualized, manipulative messaging designed specifically to exploit those recognized patterns. This isn't generic fake news. It's disinformation perfectly tailored to maximize persuasive impact on that particular audience because it speaks their language, mirrors their concerns, and exploits their known cognitive vulnerabilities. It's weaponized context.
That sounds incredibly difficult to defend against. Which brings us squarely to the need for actively addressing algorithmic bias and fairness. We need robust defenses. The sources define two main ways bias gets into these systems.
That's right. The first is sampling bias. This happens when the data used to train the AI simply isn't representative of the population it will be used on. Minority groups might be underrepresented in the data.
So the AI never really learns to recognize their patterns accurately.
Exactly. It leads to poor performance, unfair outcomes for those groups because the model is essentially ignorant about them. The second key source is institutional bias. This is different. This is where the data collection process itself is flawed or reflects historical societal biases.
Like the bias policing data example.
Precisely. Even if the data sample is large, if the way it was gathered was inherently biased, like surveillance data being collected more heavily in certain neighborhoods, then the data itself contains a skewed picture of reality. The measurements are biased from the start.
So fixing this can't just be an afterthought, right? You can't just tweak the algorithm at the end.
No, the consensus in the source material is clear. The solution must be proactive mitigation, often called fairness by design.
Meaning building fairness in from the very beginning.
Yes. Integrating fairness considerations and checks throughout the entire AI development lifecycle, starting with data collection and feature engineering, not just trying to patch bias after the model is already deployed and potentially causing harm.
What does that involve practically? What are the strategies?
It requires a multi-stage approach. First, data diversification, actively working to make training data sets more representative. This might involve collecting more data from underrepresented groups or even using sophisticated techniques to generate realistic synthetic data to fill gaps, especially where privacy concerns limit real data collection.
Okay, better data. What else?
Rigorous testing, specifically subpopulation analysis. This means you don't just look at the model's overall accuracy, you have to audit its performance, things like accuracy, false positive rates, false negative rates separately for all relevant demographic subgroups, race, gender, age, etc. The goal is equitable performance across all groups. You measure fairness by how well the system performs for the group it performs worse for.
Ensuring it works well for everyone, not just on average.
Exactly. And finally, even with the best design, sometimes things slip through or the world changes. So you also need reactive control. This involves implementing safeguards after the main model, like post-processing steps. A common example is using specialized filter models to screen the output of a large language model to catch and remove harmful, biased, or toxic language before it ever reaches the user.
Okay, so it's a continuous process. But we keep coming back to data. We established that high accuracy and fairness seem to require these massive, diverse data sets for the AI to learn robust patterns. But that creates this inherent privacy tension, doesn't it?
Huge tension. The very architectural need for vast amounts of varied data introduces significant privacy risks. The first is re-identification.
Meaning figuring out who someone is even if their name is removed.
Yes. Even if data is anonymized by stripping direct identifiers like name or address, sophisticated pattern recognition models can sometimes infer an individual's identity simply by combining enough different patterns of pseudo-anonymous data points, their unique combination of location check-ins, communication style, browsing habits, purchasing history. Enough combined patterns can become a unique fingerprint.
That's worrying. What are the risks?
The second major one is data leakage during the model training process itself. Training these huge models is computationally intensive, and there's a risk that sensitive information about individuals or specific data points used in the training set could be unintentionally embedded within the model's parameters and potentially extracted later.
Which brings us right back to that core structural trade-off.
It's unavoidable right now. Achieving high pattern recognition accuracy, and especially ensuring fairness across diverse groups, seems to demand large, rich data sets. But collecting and using large data sets inherently increases the risk of privacy compromises like re-identification or leakage.
The governance has to find a balance.
Governance has to constantly navigate this trade-off. This might involve mandating the use of advanced privacy-preserving technologies, things like federated learning, where the model trains on data locally without the raw data leaving the user's device, or differential privacy, which adds mathematical noise to obscure individual contributions while preserving overall patterns. These aim to get the pattern insights without exposing the raw individual data.
Okay, the final piece of this puzzle seems to be a robust accountability mandate. How do we ensure these systems are actually used responsibly over time?
Accountability can't be optional. It has to be structurally enforced. The sources point to several key components. First, it requires multidisciplinary governance teams. You can't leave this just to the tech developers. You need ethicists, social scientists, legal experts, domain specialists involved in setting policy and overseeing deployment.
Makes sense.
Continuous monitoring. It's not enough to audit a model once before launch. You have to keep monitoring its performance in the real world to detect concept drift.
Concept drift.
That's when the underlying patterns in the real-world data change over time. People's behavior shifts, new trends emerge. If the model isn't updated, its original learned patterns might become obsolete, inaccurate, or newly biased. Continuous monitoring catches this drift.
And critically, accountability relies on that XAI framework we discussed.
Absolutely essential. The mandate must include the required use of XAI tools. Human auditors, regulators, internal ethics boards, potentially even public interest groups must have the ability and be required to use XAI to extract and validate those local and global rules. They need to be able to check that the patterns the system is actually recognizing and acting upon remain logically sound, ethically justifiable, and legally compliant over the entire life cycle of the AI system. #tech conclusion and final thought.
So let's try to tie this all together. What's the big takeaway here? The source material seems to confirm this really profound shift driven by architectures like the Transformer. AI pattern recognition isn't just describing our past behavior anymore, is it?
No, it's moved decisively beyond that. It's become a prescriptive tool. It's actively shaping our future behavior. Think about the personalized content feeds that guide our attention, the adaptive learning systems that dictate our educational paths, the predictive risk squares that determine our opportunities. AI is now directing the flow.
And that ability to recognize these incredibly complex, long-range, multimodal patterns means AI can now derive insights like psychological profiles from spending that were simply impossible before.
And that new capability brings with it these serious systemic risks we've discussed. Algorithmic determinism, locking people into predicted paths, hyper-contextualized manipulation becoming easier, bias getting amplified at scale, especially in really sensitive areas like political discourse or access to essential services.
So the central requirement, the thing everything hinges on if we want to use this power safely and effectively, it really comes down to the ethical structures we put in place.
Absolutely. The future utility and acceptance of these powerful architectures rests entirely on establishing and enforcing robust ethical governance. That means mandating transparency wherever possible, demanding the use of explainable AI, especially those local counterfactual explanations that give individuals real agency, and embedding fairness by design principles right from the very start, back at that crucial feature engineering stage.
It needs to be built in, not bolted on.
Precisely.
Okay, so if the core power of this AI is its uncanny ability to recognize our most consistent patterns, the predictable parts of ourselves, maybe we end with a final thought for you, our listener, to consider.
How do we make sure that the governance frameworks we design are resilient enough? Resilient enough to not just tolerate, but maybe even encourage unexpected human growth? How do we allow for spontaneous change, for creativity, for the necessary, sometimes messy deviation from our own predictable historical patterns? How do we resist letting the algorithm's prediction of us become our destiny?
An important challenge to keep in mind as these systems get ever better at learning who you are. Thank you for joining us on The Deep Dive.
Searching for answers to unanswered questions.
This is DigitView.